Welcome to the deep dive. You've sent over, well, quite a significant document, the NVIDIA DRIVE OS Linux SDK Developer Guide.
It's definitely not light reading.
No kidding. So our job today is to act as your guides, really, through this pretty dense technical landscape. We want to help pull out the crucial insights, without getting totally lost in the weeds.
Exactly. Think of it as a shortcut to getting informed. This guide is the manual for building autonomous vehicle applications on NVIDIA's DRIVE Orin platform.
Right, the system on a chip. And you could probably spend weeks digging through this and still feel like you're just scratching the surface.
Oh, easily.
Weeks.
So our mission for this deep dive is to take that fire hose of information and really distill it down.
Yeah.
We want to shed light on the core concepts, the foundations, and also the practical bits that really matter if you want to understand how these AV apps actually come together on DRIVE Orin.
Yeah, avoid that information overload because this guide covers, everything from the absolute basics, bootloaders, virtualization, setting up isolated environments.
All the way up to using industry tools like NVIDIA, CDA, TensorRT, and of course all the critical security stuff baked in.
Okay, let's start right at the beginning then. Fundamentally, what's this SDK for, and what are the main pieces that make it tick?
So at its heart, it's laser-focused on developing applications for autonomous vehicles, specifically using that NVIDIA DRIVE Orin chip. It's a very specialized toolkit.
Right.
And it really rests on two main pillars. First, you've got the DRIVE OS foundation. That's like the bedrock, bootloaders to get things started, a hypervisor.
The hypervisor, yeah, like a traffic cop for the hardware.
Exactly. That's a good way to put it. It lets multiple independent operating systems run side by side safely. And the virtualization tech itself is part of that foundation.
Okay, so it creates these secure, isolated spaces. What's actually running inside them?
That's the second pillar.
Yeah.
The guest OS virtual machines. These are the operating systems running within those virtual spaces. And crucially, the guide points out these are Linux OCs.
Ah, Linux. Makes sense. It's used everywhere in embedded systems.
Definitely. And here, it's used for both the low-level system functions and for developing and running the actual autonomous driving applications.
Okay. Now, we always hear about NVIDIA's CUDA and TensorRT. Where do they fit into this DRIVE OS picture?
They're absolutely integral. They provide these, industry standard ways to seriously accelerate compute tasks, especially parallel processing, machine learning, that kind of stuff.
Right, the heavy lifting.
Yeah. But here's a really, really important point the guide makes clear. The versions of CDA and TensorRT in DRIVE OS 6.0. They are specifically designed and optimized just for the automotive drive AGX Orin platform.
Oh, okay. So you can't just grab these and use them on like a desktop GPU or something.
Nope, not compatible. They're meant purely for use within this DRIVE OS ecosystem on the Orin chip. It's a trade-off, right? You get that tight integration and optimized performance, but you're committing to the DRIVE OS environment for those specific accelerated tasks in your AV application.
Got it. Very focused, very optimized. And the main OS itself, what's the sort of reference baseline developers work with?
The primary OS is NVIDIA DRIVE OS 6.0. The guide really positions it as a safe, secure execution environment, which, has to be the top priority for self-driving cars, right?
Absolutely paramount.
And it comes packed with essential services. Secure boot to make sure nothing's been tampered with, security services, a firewall, and importantly, mechanisms for over-the-air updates. OTA is vital for keeping these complex systems maintained and updated out in the real world.
Okay, foundation's covered. Now let's picture someone actually, getting their hands dirty with this, booting it up. What are some of the first hurdles they might hit? And does the guide help out?
Oh, yeah. One of the very first things is just getting the software onto the hardware, a flashing process. And good sign, the guide actually has a dedicated troubleshooting section just for this.
Well, that's smart. Always appreciate that. What kind of problems does it address?
Well, the classic one. The flashing just fails.
Wow.
Doesn't complete.
Oh, yeah, been there.
So it suggests some basic but often effective fixes. First, try reseating the USB cable. And it specifically calls out using the LFT USB Type-C port on the Orin device. That detail matters.
Okay, the left port. Good tip.
Then it suggests trying different USB ports on the host computer. Maybe try a USB 3.1 port if you have one. Or even try different USB cables, higher speed maybe, or sometimes counterintuitively, even a USB 2.0 port might work better.
Huh. So USB connectivity can be a bit finicky even with this high-end gear.
Apparently so. It's worth trying those simple things first.
Definitely. Now, the guide also mentions connecting to something called the Oryx MCU console. Why would a developer need to do that?
Right, the Oryx MCU. That's a separate, dedicated microcontroller on the D-Drive AGX platform. The guide shows how to connect using sudo minicom-w-ddlu davd-acm1.
Okay, Minicom standard serial terminal.
Exactly. And once you're connected, it gives you a couple of commands. Tegra recovery by 1 on and then Tegra set by 1. These likely put the main Tegra X1 processor, part of the bigger Orin system, into a special recovery mode.
Ah, so it's a way to get the chip ready for low-level stuff like flashing or debugging if things go wrong.
Precisely. It's kind of a backdoor to get it into the right state before you flash the main software.
And the command for that main flashing process.
The core command detailed is tools flash tools bootburn bootburn.py board variant b board variant bqai.
Okay, so bootburn.py. And that board variant depends on your specific hardware, I guess.
Yep. Different Orin boards will have different identifiers there, and the -BQSB flag. That probably means you're flashing to the quad SBI flash memory chip on the board.
Makes sense. Now, there's a little note in there about using sudo or not using sudo consistently with some of these tools like bootburn. What's that about?
Ah, yeah, that's a good catch. It points out you don't have to use sudo with bootburn.py or create simpitches.py or flash bspimpches.py. But, and this is the key part, it strongly advises that if you use sudo for one, you should use it for all of them.
Ah, consistent.
Exactly. Don't mix and match using sudo and not using sudo for these specific commands.
Yeah.
It probably helps avoid weird permission issues or inconsistencies during that pretty delicate flashing operation.
Right. Consistency is always good with system-level stuff. So, flash complete. What's the first boot experience like? Out of the box.
Okay, so the guide outlines a few steps. First up, you'll need to accept the EULA, the End User License Agreement. Standard stuff.
Yep. Click accept.
Then you set up administrator username and password for the system. Now, it clarifies this is mainly for the very first boot of a fresh device. If you flashed using, say, the NVIDIA SDK manager or a Docker setup, you might not see this unless you wiped persistent data.
Okay, so potentially a one-time thing in many setups. What's next after the user setup?
Then you choose an SSH profile.
Yeah.
SSH, secure shell, or for remote access.
Standard secure login, yeah.
DriveOS Linux gives you two options here. One is an NVIDIA enhanced security profile. Uses more modern, robust ECDSA algorithms for the key exchange. More secure. Or you can choose a profile that's more like a standard Ubuntu 18.04 setup. But the important thing is, whichever you choose, the SSH server is enabled by default on the Orin target.
Oh, nice. So you can log in remotely right away after that first boot. Convenient for development.
Definitely. But there's a wrinkle depending on how you flashed it.
Ah, okay. How so?
If you got a dev kit that was pre-flashed by NVIDIA, SSH is usually already installed and good to go. But if you flashed a more minimal base image, like using the DriveOS core file system.
Right, like a bare bones Debian build.
Exactly. Then the SSH server might not be included by default. You'd need to install it manually. However, if you use a more feature-rich image, like DriveOS Ubi Desktop, then SSH is enabled by default.
Okay, so the specific image you flash matters for whether SSH is there from the start. Good to know. The guide also mentions adding users to the debug group. Why is that needed?
Yeah, for certain things, especially graphics-related stuff, like running graphics samples or accessing GPU performance profiling data. Yes, the user needs to be a member of that debug Linux group. The guide doesn't go deep into the why, the technical reason, but flags it as something developers will likely need to do to enable those activities.
Okay, a permission thing for specific tools. And if you need to remove a user later,
It gives the command, sudo to loser backup remove home user. And notice those flags backup creates an archive of their home directory first.
oh, handy.
And then remove home actually deletes the home user directory. So it's pretty clean removal.
Right, gets rid of the account and their files with a backup just in case.
Okay, initial setup makes sense. Let's talk networking. Super critical for AVs. How do you usually set up the connection to the Orin device?
The guide mostly talks about setting up a static IP address, but on your host machine, your development computer.
Ah, on the host, not the target.
Yeah, for that direct connection during development. Static IPs are usually more reliable than DHCP for this kind of thing. It explains the standard Linux way. Modify the xset network interfaces file on your host. Okay, xset network interfaces. Standard Linux network config. And you'd need admin rights for that, right? Sudo?
Absolutely. That file's usually read-only for normal users, so yeah, sudo with your favorite text editor.
Got it. What kind of connection setups does it give examples for?
It shows two common ones. First, if your host machine has like a second network card, you plugged in a separate network adapter, you add lines for that interface, maybe if1, set it to static, and give it the IP address, netmask, gateway you want.
Standard static IP config. What's the second scenario?
Using a USB Ethernet adapter to connect the host to the Orin, the static IP part is similar, but there's an extra line it highlights. Post up at cnet.disk-dhtp-server restart.
Huh. Restarting the DHCP server. Why is that needed for USB Ethernet?
Good question. It might be necessary to make sure the DHCP server on your host, if it's running one, properly recognizes and handles the new USB interface after it comes up. Could be crucial for the connection to work right in that specific setup.
Okay, that's a subtle but potentially important detail for USB connections. The guide also mentions a tool called common-if-to-stap. What's that for?
Yeah, common-if-to-stap. It's described as a command line tool to verify and test features of the common interface within Drive OS.
Okay, like a diagnostic tool?
Seems like it. Running it with HE lists all its commands. It gives a couple examples. Hashtag common-if-to-stap-macure set seems to reset the whole board.
Whoa, okay.
And hashtag common-if-to-stap-tick-reset by 1 just resets the Tegra X1 processor. So yeah, it's like a handy utility for basic system control and maybe checking if different hardware bits are responding.
Right. Now, what about networking specifically in safety-critical setups? Does the guide mention anything special there?
Yes, definitely. It highlights several key things for safety platform configurations. First, to meet really strict time synchronization goals, the CPU inside the Marvell network switch chip and its firmware are actually disabled.
Disabled? Why?
Probably to guarantee deterministic behavior and avoid any potential interference with the critical time sync protocols running directly through the switch hardware.
Okay, makes sense for safety. What else?
The MTU size maximum transmission unit on some of the network switches, MGBE2 and OK, is reduced, down to around 1,500 bytes.
Why shrink the packet size?
To minimize latency for the PTP bypass. PTP is precision time protocol, crucial for that accurate time sync across the vehicle network. Smaller packets mean less delay getting through the switch hardware path.
Got it. Latency reduction. Any other safety considerations?
Yeah, because that Marvell switch CPU is disabled, you lose over-the-air update capability specifically for those network switches. Updates would need a different mechanism.
Okay, so safety means some trade-offs in features like OTA for certain components. There's also a big warning about compatibility between the Tegra software and the RX network config. What's the deal there?
This sounds absolutely critical. The guide really hammers this point.
Ah.
Developers must manually ensure the network settings programmed into the RX microcontroller perfectly match what the software or the running on the main Tegra Orin processor expect.
Manually. There's no automatic sync?
Nope. Explicitly says no automatic synchronization. And if there's a mismatch, if ARX is configured one way and Tegra expects another way based on this thing called the Orin Platform Configuration Table or PCT, it can lead to undefined behavior, which in a car is, really bad. So meticulous configuration, double-checking, testing, absolutely vital. No cutting corners here.
Wow, okay. That's a huge responsibility for the developer to get right.
The guy then gets specific about a particular board, the P3663. What are the networking highlights there?
Right, for that P3663 board, it points out a couple of connectors. There's a dual HMTD connector J2. It has two Ethernet interfaces. One goes straight to the Orin SOC's own Ethernet controller, MGB-V0. The other connects to a separate PCIe Ethernet chip, a LAN 7431.
And then there's a MateNet connector, J11. That connects to various ports on an integrated network switch chip, an 88Q5072. Just details so developers know the physical hookups on that specific board.
Got it. Board-specific hardware details. And for setting up to CP, that precision time protocol, it mentions a tool, GPT-PT-Sync. How does that work?
GPT-PT-Sync is the main tool for PTP configuration. The example command looks like sudo.gpt-pt-sync interface -f autosar-cfg.ini plus a bunch of other flags for timing parameters.
Okay, so you pointed at a network interface like equals0 or ngb0.
Right. Replace interface with the actual interface name. And -daf autosar-cfg.ini means it reads the detailed PTP settings from that INI file.
An INI file for config. Any gotchas there?
Yes, one very specific one. Inside that INI file, there's a parameter follow-up date list. The guide emphasizes the values for this must be in decimal format, not hex, which is often used elsewhere.
Oh, that's exactly the kind of detail that could trip someone up for hours. Decimal, not hex. Got it.
Definitely. Get that wrong, and PTP probably just won't sync correctly.
Okay. And choosing the actual PTP source, the master clock.
That selection specifically the MSC address of the time source, is configured through settings in the NVPPS and NVTime2 modules. Those are the software interfaces for the timing hardware.
NVPPS, pulse per second.
Yeah, NVIDIA pulse per second. And it also notes that from release 6.0.3 onwards, a feature that locks one of the Ethernet controller clocks, MGBE2, to the system's timestamp counter, TSC, is enabled by default at boot. Helps keep the time base stable.
Okay. Speaking of NVPPS, the guide calls it a kernel module. What's its main job?
Its main role is to give user space applications a single, consistent way to ask, what time is it? According to the hardware synchronized PTP clock. This comes from the precision hardware clock, or PHC.
So one place to get the official PTP time.
Right. And it also lets apps get timestamps for events that are correlated between both the PTP time and the system's own TSC time. Super useful for accurately lining up events across the system that depend on precise timing. And yeah, it's enabled by default in the kernel.
Sounds fundamental for any time-critical stuff. The guide even shows a code snippet for network config. What's that illustrating?
It's a basic example of how a user space app talks to the kernel to set up network parameters, specifically for EST Ethernet switch time synchronization.
Ah, the time-aware switching.
Exactly. It shows opening a network socket, defining a C structure, OECS config, to hold the EST settings, filling that structure from user input, and then using the IOCTL system call.
IOCTL. Input-output control, low-level Linux stuff.
Yep. You package up your config data and a command code, like ethercfg, into another structure, different data struct, and make the IOCTL call on the socket. That sends the command and data down to the network driver in the kernel to actually apply the settings. Then you close the socket. It's a glimpse into how user space configures kernel-level network features.
Cool. Good to see the underlying mechanism. It also mentions MCAC maxen, maxx index, and maxsec exhaustion. What area do these relate to?
Those are all about MCSec. That's the standard for link layer Ethernet security, encrypting traffic right at the Ethernet level.
Okay, security. So what are they specifically?
MCAC is the MHCSec Key Agreement Connectivity Association key name. Basically, a shared secret name, 32 bytes long, used to set up a secure connection between two devices.
Right, like a password for the secure link.
Sort of, yeah. maxx index is used if the device is acting as the key server in the MKA protocol. It picks the encryption algorithm 0 for GCM AES 128, 1 for GCM AES 256.
Cipher suite selection. Got it. And the last one, maxsec exhaustion.
Also for the key server, it sets how many packets can use the current encryption key before you have to generate a new key. It prevents reusing packet numbers, which is a security risk.
Forcing rekeying periodically. Makes sense.
And if you're troubleshooting XCSec, the guide mentions the NVMe CSec driver have error counters and stats you can read using DECTPLs with the command msg.i.dcmd. SIOCGDRV spec. Lets you check the link.
Okay, good tools for debugging secure links. Let's shift focus slightly to key software concepts and APIs. The guide defines TC, GCL, RQ. Can you break those down? They sound important for real-time networking.
Absolutely fundamental, yeah, especially for QoS and time-sensitive networking, TSN. TC is traffic class. Network traffic gets sorted into different classes, usually 0 to 7, so you can prioritize critical data.
Right, like sensor data gets higher priority than, say, infotainment updates.
Exactly. GCL is gate control list. This is core to TSN, specifically the 802.1 QBV standard. It's a schedule, defined precisely in time, that dictates when each traffic class is allowed to transmit onto the network. Like traffic lights for data packets, timed down to the microsecond.
Wow, okay. Very precise control. And RQ?
RQ is frame preemption residue queue. Frame preemption lets a high-priority express frame interrupt a lower-priority frame mid-transmission.
Cuts in line, basically.
Yeah. The interrupted part of the low-priority frame gets temporarily parked in this residue queue. Once the express frame is gone, the low-priority frame resumes from where it was interrupted. The guide notes Q of E is always the express queue and can't be used as an RQ.
Got it. Default express lane. And it also defines APP OS DUT.
Just common acronyms. Application, operating system, and device under test. You'll see those a lot in technical docs.
Right. Now, IOCTL interfaces again, we saw an example, but can you explain their general role for hardware config in Linux?
Sure. IOCTL, input-output control, is really a fundamental Linux system call. It's the standard way for user space applications to send commands directly to and get information from kernel device drivers.
So app talks to driver via IOCTL.
Pretty much. The pattern is, open a device file or socket related to the hardware. Prepare a data structure holding the command code and any necessary data. Make the IOC system call, passing the file descriptor, the command code, and the data structure. The kernel routes this to the right driver. The driver does the action, like setting a hardware register, maybe return some data, and the call completes. Then you usually close the file descriptor. It's how user space controls hardware indirectly through the kernel.
Okay, that makes sense. And building on that, there's a specific sample app mentioned, or there's the sample app for configuring EST, that time-aware switching. What's the syntax look like?
Right, the NVIDIA sample lib. It's a command line tool specifically for setting up EST. The syntax is shown as NVIDIA sample app interface. It's enable disable base time offset cycle time num GCL entries.
GCL entries.
Whoa, okay, lots of parameters. Yeah, it gives you fine-grained control. Enable disable is 1 for on, 0 for off. Base time in hex nanoseconds and base time offset in decimal seconds. Set the start time for the GCL schedule. Cycle time, hex nanoseconds, is how long one schedule loop lasts. Then you say how many entries are in your schedule, num GCL entries, and provide the actual entries, GCL entries, which define the time windows for each traffic class.
Very detailed control over the network timing. It also lists some status indicators related to EST, like HIBFQ, base time reserve, SWN list complete. What do these tell you?
They give feedback on how EST is running, HIBFQ3 through HIBFQ7. Those sound like head-of-line blocking counters for traffic classes 3 through 7. They'd increment if traffic in that class is getting stuck, maybe waiting for its scheduled window.
Okay, indicates congestion or scheduling issues.
Probably. Basetime Sager would likely be a flag saying there was an error setting the schedule's start time. Maybe you tried to set a time in the past or something invalid.
Right, and SWN list complete.
That sounds like a counter that increments each time a full gate control list cycle finishes successfully. Like the schedule completed one loop as programmed. The guide even gives an example command using NVIDIA sample lib to turn EST on with a specific cycle time and some GCL entries, showing how you'd use it practically.
Great. Helps connect the parameters and status flags. Let's pivot back to flashing the device, but focusing on customization. The guide mentions boot burn, kernel, pre-build, offline binaries, and specifically boot burn options. How can you tailor flashing with boot burn?
Boot burn, the main flashing tool, has quite a few command line flags for customization. DexBar forces RCMBO, that's recovery mode boot, useful if things are really messed up.
Okay, recovery mode.
Uppercase DEP-T enables detailed tracing. It dumps logs, like logtrace.txt, in the boot burn directory. Very helpful for debugging flash failures.
Tracing, always good.
U lets you provide a custom config file for UFS provisioning that's universal flash storage. -V is important. It enabled read-back verification. After flashing, it reads the data back from the device and compares it to the source files to catch errors.
Oh, verification. Definitely want that.
And customer data lets you inject specific data, like serial numbers or factory settings, into certain partitions during the flash. It also notes that ZAG and AA flags are obsolete now.
That customer data sounds really useful for manufacturing. How does it work?
You give it a path to a JSON file containing your data. Optionally, you can also provide a JSON schema file to validate your data's format. Boot burn can even do partial updates, so you only need to provide the field you want to change in the JSON. It shows examples of using this flag with bootburn.py itself, and also with a higher level creates bispimages.py and flashbaseimages.py scripts.
Okay, JSON for custom data, flexible. What about specifying Linux or QNX images or signing keys?
Yep, flags for those too. Lowercase $ol tells bootburn to handle Linux images. -Q is for QNX images. -P lets you point to your private key file, RSA or ECDSA, used for signing the boot components, bootloader, kernel, BCT, etc. That's crucial for secure boot.
Right. Signing ensures authenticity.
An encryption key provides the key if you're using encrypted secure boot. It also mentions the default config files bootburn uses. QuickBootQSpyLinux.cfg for Linux and QuickBootQSpyLinux.cfg for QNX. These files control the default flash process.
So lots of knobs to turn for flashing and security. And when you run the main flashbaseimages.py script, what's happening underneath? What other scripts or tools does it use?
That main script orchestrates several others. It calls bootburnlib.py, probably the core library, bootburnadb.py, likely for using Android Debug Bridge, maybe for post-last steps, and bootburnhelper.py, various utility functions.
It's like helpful scripts.
And it uses lower-level command line tools, too. Tegra CMV2, NVIDIA's tool for talking to Tegra in recovery mode, the standard AB, something called NVDD, maybe an NVIDIA device driver tool, and NVSCUinfo, to get hardware SKU info. It even tells you where flashbaseimages.py usually lives in the file system.
Okay, that paints a clear picture of the flashing toolchain. Let's switch to graphics and display. Big topic. What are some key recommendations from the guide for optimizing graphics performance, say with OpenGL ES?
Yeah, performance is always key. One big area is optimizing vertex attributes, the data you send per vertex, like position, color, texture coordinates.
How does that help?
The GPU has a vertex cache, the pre-TNL cache, but its capacity is based on bytes of attribute data, not number of vertices. So if you send huge amounts of data per vertex, you blow out the cache really quickly, forcing the GPU to refetch data, which is slow.
Ah, so smaller vertex data means better cache usage.
Exactly. The guide strongly recommends reducing the size of each attribute and the number of attributes. Use smaller types, like bytes or shorts, instead of full 32-bit floats if you don't need the precision. Maybe even half floats. Per vertex color or texture chords can often use smaller types too. Less data per vertex equals better cache efficiency.
Makes perfect sense. Use the smallest data type that works. What about buffer objects, where this vertex data is stored?
The default usage flag when you create buffers is static draw. The guide says most of the time this will actually give the fastest GPU access. And importantly, static draw doesn't mean you can't ever update the buffer.
Oh, right. It's more of a hint to the driver, isn't it?
Exactly. It just tells the driver you intend to update it infrequently. Even if you update it every few frames, static draw might still be the best. The guide warns against switching to dynamic draw or stream draw without careful benchmarking, because it can sometimes hurt performance if used incorrectly.
So stick with the default unless you prove otherwise with data. Good advice. What about shaders, the GPU programs?
Efficient shaders are critical. Treat them like your innermost CPU loops. Every instruction counts because it runs potentially millions of times per frame. Avoid unnecessary calculations or conditionals.
Right. Optimize the shader code itself.
Well, yes, but the guide also says, before you start micro-optimizing shaders, make sure you're doing the big stuff right. Are you culling geometry on the CPU that's outside the view frustum? Don't waste GPU time on invisible stuff. And are you generating way too many fragments by overdrawing? Fix those higher-level issues first. They often give bigger wins than shading cycles off a shader.
Good point. Optimize the pipeline before the micro-optimizations. Textures are often bottlenecks too, right?
Huge bottlenecks. The guide heavily pushes texture compression. Big benefits. Less memory bandwidth used transferring them to the GPU, faster downloads, and much better texture cache efficiency.
What formats does it recommend?
It mentions S3TC for general color images, especially those with smooth gradients. And LATC can be good for things like normal maps. Using compression might even let you use higher-res textures without killing performance. And importantly, you can compress textures offline using tools from NVIDIA's developer site, so you don't take a runtime hit.
Offline compression, definitely the way to go. Any other texture tips?
Yeah, update textures sparingly. Ask yourself, does this texture really need to be updated every single frame? Things like environment maps or shadow maps might be fine updated less often, saving significant bandwidth. Also, consider power of 2 versus non-power of 2 textures. NPOT can sometimes be more memory efficient for large textures.
Reuse textures, update less often. Got it. What about reading back the frame buffer contents? Sometimes apps need to do that.
The guide warns against doing that frequently. It forces the GPU pipeline to flush, stalls everything, and kills CPU-GPU parallelism. Bad for frame rates.
Okay. Avoid if possible. What if you have to?
Do it minimally. Maybe just once at the very beginning of the next frame. And if you only need a small part of the screen, look into the pack-subimage extension and the pack-a-row-link pixel store parameter. They can make reading subrectangles more efficient than grabbing the whole thing.
Strategic readbacks only. Got it. It also mentions memory banking for video memory. What's key there?
Modern GPU memory is banked for parallel access. For certain things, like MIP map textures at different resolution levels, placement matters. Often, alternating MIP levels must be in different banks for efficient fetching. Also, different memory regions might have alignment restrictions, maybe to match host CPU pages for faster transfers or for better DMA or display scan-out performance. The memory allocator might also have its own rules to improve performance. It's about understanding the underlying hardware architecture a bit.
Okay, memory layout matters for performance. Let's talk EGL stream. What is that and why is it useful here?
EGL stream is basically a high-performance, low-latency pipeline for moving image frames or other data between different parts of the system. Think API to API, like from OpenGL-ES to SDK or NVIDIA to OpenGL.
A data pipe.
Exactly. You have a producer putting frames into the stream and a consumer pulling them out. It's super useful in complex AV pipelines where maybe a camera, NVIDIA captures data, the GPU, CDA processes it, and that goes to the display, OpenGL. EGL Stream lets you hand off the data efficiently without expensive memory copies.
Nice. Avoids copies. What about setting application time slices? The guide gives some advice on that.
Yeah, how much CPU time an app gets in each scheduling interval. For high-priority real-time apps, the goal is to give them a big enough time slice to finish their critical work within that one slice.
How big is big enough?
It even gives a formula as a guideline for a single high-priority app aiming for 60 Hz, 16.6 meters. It subtracts time for lower priority tasks, example uses 1.5 liters, context switch overhead, and CPU round-robin time. Correct. The example comes out around 11.6 meters as a recommended upper bound for the time slice. It's about ensuring critical tasks get enough CPU time to meet deadlines.
A quantitative guideline, that's helpful. Now, the guide gets very specific on running the VK-Cube Vulkan sample with Wayland and X11. What are the basic steps?
Okay, for VK-Cube with Wayland, first, load the NVIDIA-DRM.Keras kernel module with mod setting enabled. Then, set up the XDG or ontomedia environment variable pointing to a directory for Wayland's runtime files. Start the Weston Wayland compositor in the background. Finally, go into the VK-Cube Wayland directory and run .vkcube. You can add C frame count to run for a specific number of frames.
Okay. And for X11?
Simpler, in a way. Make sure other Windows systems like Wayland aren't running. Go to the VK-K11 directory and run .vkcube. Pretty straightforward.
And there's another Vulkan sample, VK01 trihost, meant to run on the host machine. What's needed for that?
Right, running on your development PC, you need the desktop Vulkan SDK 1.2 plus, the NVIDIA Vulkan driver for your desktop card, and the vClaire Chronos Songan library must be available.
Okay, Vulkan setup on the host.
Then, navigate to the samples build directory. You usually need to set two environment variables, vClaire path, pointing to where your Vulkan layer libraries are, and VK-JSON file path, pointing to the layer manifest JSON files. Once those are set, you can just execute VK01 trihost.
Setting those layer paths is often key for Vulkan dev. What about screen orientation? Can you rotate the display in Drive OS?
Yes, using the Weston Wayland compositor, you edit the weston.ini config file. In the output section for your display, or LVDS1, there's a transform option.
What can you set it to?
You can use 90, 180, 270 for clockwise rotation, or keywords like flip orthogonal, flip vertical, or combinations. The guide shows an example setting, transform in your 90-degree rotation.
Handy for different mounting orientations. It also mentions Weston creates its socket in sexdgredinadir. Why is that directory significant?
Sexdgredinadir is a standard Linux thing. It's where apps are supposed to put temporary, user-specific runtime files, like sockets. Weston puts its communication socket there, so Wayland client applications know where to find it to connect to the compositor. It's just following the standard convention.
Okay, standard practice. How does Weston's OpenGL renderer handle image buffers internally? It mentions DMA-BUF.
Right. It uses DMA-BUF for efficient buffer sharing. When an app renders, Weston gets a DMA-BUF handle. It uses EGL extensions, EGL extimage the MOBIF important modifiers, to wrap that DMA-BUF handle to an EGLimage object.
An EGL wrapper for the buffer.
Yep. Then it queries the buffer's properties, like memory layout tiling, using another extension, Eagle Query Demovus Modifiers EXT, to figure out the right OpenGL texture target. Finally, it binds the EGLimage to an OpenGL texture, making the app's rendered frame available to the compositor without needing a memory copy. It's all about efficient sharing via DMA-BUF.
DMA-BUF for the win. It also mentions support for GNOME Wayland and lists relevant EGL extensions. What are those needed for?
To support a more complex desktop like GNOME on Wayland, compared to the simpler Weston, you need a bunch of EGL extensions. Things for discovering the graphics hardware, EGL device, EGL STI device base, etc., managing displays, EGL output, and crucially, EGL stream extensions, EGL KHR stream producer consumer extensions, for that efficient data transfer between components within the GNOME environment. The guide links to the Chronos specs for details.
So EGL extensions are the building blocks for Wayland support, and EGL stream remains important. What if you're rendering without any Windows system? It talks about a stream surface.
Yeah, if there's no Wayland or X11, you need a way to get pixels onto the screen. A stream surface acts like a regular EGL rendering surface, EGL surface. You render to it, call eagle swap buffers.
But where do the buffers go if there's no window?
That's the trick. The stream surface is also an EGL stream producer. So eagle swap buffers doesn't present to a window. It pushes the rendered frame onto the EGL stream. Then, typically, an EGL output consumer connected to the display hardware pulls frames from that stream and puts them on the screen. It's a way to link rendering directly to the display via EGL stream when no window system is involved.
Clever. A virtual target feeding the display stream. Lastly, for graphics, NVIDIA's config for basic X server setup. Any key options mentioned?
It points out the standard help commands,
Yeah.
NVIDIA Xconfig help and advanced help to see all the options for generating modifying the xorg.conf file.
Okay.
It also highlights one specific xorg.conf option, Tegra overlay blend mode. Set in the device section, it controls how the X server's hardware overlay plane blends with the background. You can have opaque, default disk covers, source alpha blend, standard alpha blending, or pre-mult source alpha blend for pre-multiplied alpha. This only matters if something else has already put a layer behind the X output.
Okay, controls for overlay blending in X11. That covers graphics pretty well. Let's move to power management and system control. What's the shutdown process like?
The guide describes a safe shutdown sequence. When initiated, the system waits for a specific GPIO signal from the Orin sauce before actually powering off,
Waits for a signal. Why?
probably to allow Orin to finish critical tasks gracefully before the power is cut. But there's a timeout. If the signal doesn't come within a configurable time, the shutdown might abort or go into an error state, preventing it from hanging forever.
Fail-safe timeout. Good. What about low power states?
It mentions support for Orin's suspend mode, called SC7. It's a low-power state you can trigger using shell commands sent from the Oryx MCU.
Okay, controlled shutdown and suspend support. What about the main Orin power management component, its functions?
It handles the basics, powering Orin on and off. It also sets up specific GPIO pins during boot that configure how Orin starts. Interestingly, it's described as mostly stateless.
Stateless? What does that mean?
It doesn't really keep track of the power state itself. It just reacts to commands it gets from software running on the Oryx MCU. It also monitors hardware power goods signals during power-up. If it detects a failure, it aborts the power on to prevent damage.
Okay, listens to commands and monitors hardware health. There's also a fan control component mentioned. How does that work?
It's a reference software piece. It periodically reads the fan's actual speed,
Hmm.
RPM, from the Oryx MCU and compares it to the requested speed to check for faults.
Okay, monitors the fan. How does it decide the speed?
It gets temperature data from Orin sensors over Ethernet. By default, it picks the maximum temperature from usually 3 sensors and adjusts the fan speed based on that. But the logic for choosing which temperature to use can be customized by modifying a function called MCUSWC4 for fan-controlled shoes temperature.
Ah, customizable thermal control logic. Makes sense. Lastly here, NV display components. OpenWFD, NVKM, serializer, roles.
NV Display is the overall subsystem. OpenWFD, Open Windowing Foundation Display, is a Kronos API standard. It's a low-level hardware abstraction. Windows systems or apps use OpenWFD to talk to the display hardware in a standard way.
So the API layer for apps?
Right. In VKMS, NVIDIA-mods.tarco, is the kernel driver. Kernel mode setting. It manages the display hardware at the OS level setting modes, frame buffers, video output.
Kernel driver. And serializer.
Those are kernel modules, MaximFSL, TIFF-Link, that talk to the serializer chips. These chips convert the GPU's digital display signal into formats like GMSL or FPD-Link, the high-speed serial links often used to connect to automotive displays.
Got it. API, kernel driver, May serializer, chip driver, kernel physical link. Okay, let's dive into data handling and streaming. NVSciBuff comes up first. What's its main job?
NVSciBuff is all about efficiently allocating and sharing memory buffers between different processes and hardware engines on Orin. Then camera data going to the GPU, then maybe to a DLA, then maybe getting encoded.
Sharing buffers without copying?
Yes, exactly. Avoids performance-killing copies. It's crucial for those complex pipelines. But the guide notes a limitation currently. With attribute lists for these buffers, you can really only mix image attributes and tensor attributes. And if you do mix them, the tensor attributes have to be filled using NVMedia APIs for things to reconcile properly.
Okay, some rules about mixing metadata types for shared buffers. How does it manage when different components have different requirements for the same buffer?
That's called reconciliation. An app calls NVSciBuff Attribute List Reconcile. All the components using the buffer, producers, consumers, provide their requirements, size, format, alignment, etc. NVSciBuff tries to find a set of attributes that satisfies everyone. If it succeeds, they all agree on the buffer's properties and can use it safely.
A negotiation for buffer specs makes sense. Building on that is NVSciStream. What extra layer does that add?
NVSciStream sits on top of NVSciBuff and NVSciSync for synchronization. It provides higher-level tools and abstractions specifically to make building complex streaming applications easier, especially if you have multiple stages, maybe developed by different teams. It helps manage the data flow, sync, and communication between all the different blocks in the stream.
So simplifies building more complex multi-stage pipelines.
That's the goal, yeah. handles some of the boilerplate and complexity.
But can you do simple streaming without NVSci Stream?
Oh, definitely. The guide gives a simple stream example, like camera, NVIDIA, sending frames directly to COD for processing. In that case, you might just use NVSci directly to create one shared buffer.
And synchronization.
You could just use a couple of NVSci sync objects directly. One for NVMedia to signal frame ready, another for CO to signal frame processed. For simple point-to-point, NVSci stream might be overkill.
Okay, so NVSci Stream is for the more complex multi-block, multi-type streams. Speaking of types, it mentions element types in NVSci Stream. What are those?
In a complex stream, a producer might send different kinds of data: raw images, processed images, metadata. Element types are just integers defined by the system architect to tag each kind of data.
Like labels for the data packets.
Exactly. So consumers can say, I only want element type 3 processed images, or I need type 1 raw and type 5 metadata. It allows filtering and routing within the stream.
Got it. Tagging data. How does a basic NVSci Stream block behave during setup and then during actual streaming?
During setup, a block mainly reports the data packets allocated to it. During streaming, it manages those packets. It signals when a packet is free to be reused. A producer retrieves an available packet, maybe waiting on a sync fence first, fills it, and then accepts it back into the stream, potentially attaching another fence to signal when the data is ready for the consumer.
Okay. Manages packet lifecycle and sync. What about dynamic changes, like changing image resolution on the fly?
The guide mentions that in non-safety builds, there's limited support for requesting attribute changes during streaming. The block would report the new attributes and buffer allocations, deallocations. However, it explicitly states that actual buffer reallocation during streaming is generally not supported in this release for non-safety builds.
Ah, okay. So dynamic changes are tricky or not fully supported right now. What if one producer needs to send data to multiple consumers, multicast blocks?
Yep, multicast blocks handle that one-to-many scenario. The block takes the producer's output and fans it out to all connected consumers. The consumers don't usually know they're part of multicast. The producer sees the multicast block as a single virtual consumer representing all the real ones.
Convenient. Any drawbacks?
Big one. The guide warns that multicast blocks offer no inherent fault isolation. If one consumer misbehaves or crashes, it could potentially disrupt the entire stream for everyone, including the producer and other consumers. For safety security, you'd need extra mechanisms beyond a simple multicast block.
Okay, so easy fan out, but no built-in protection between consumers. What about streaming between different processes that don't share memory? Memory boundary IPC blocks.
Exactly. If your producer is in process A and consumers in process B, they don't share memory directly. The IPC block handles this. Process A gets a packet, fills it. The IPC block transmits the data, often involving a copy, across the process boundary to process B, where it goes into a packet owned by process B. Process A can then reuse its original packet without waiting for B to finish. Requires setting up auxiliary communication channels between the processes.
A copy-based bridge between processes. Got it. It also briefly mentions limiter blocks and present sync blocks.
Limiter blocks just control the flow rate. You can set a maximum number of packets allowed downstream at any time. Prevents a fast producer overwhelming a slow consumer. Present sync blocks are for synchronization, likely helping coordinate when frames are actually presented, ensuring correct timing or order.
Flow control and sync points. Makes sense. There's also the NVSci event service. What does that do?
It's a central API for waiting on multiple event notifications simultaneously. These notifications can come from NVSci stream blocks or from other drivers or modules in the system that support NVSci event notifier objects. It lets an app wait for different kinds of events from different sources all in one place. Very useful for building responsive event loops.
A unified event waiting mechanism. Cool. Yeah. What about connection-disconnection events within NVSci stream itself?
The first event a block usually gets is NVSci stream event type connected. Means the pathway is fully established. Critically, the guide says no operations are allowed on a block before this event. You have to wait for it. There are also disconnect events if the stream breaks, allowing cleanup.
Okay, wait for connected before doing anything. What's the element import process it describes?
After producer and consumer agree on the data element characteristics, format, size, etc., they both need to signal readiness to actually exchange packets. They do this by calling NVSci stream block setup status set, with the status NVSci stream setup element import. It's like a final handshake. Okay, I understand the data format. I'm ready to receive send-up packets now. It also mentions some details about how this works with secondary pools connected via IPC blocks.
Handshake complete. Ready for data. How does a producer actually get packets and put data in them?
A producer can often get multiple empty packets at once from its pool. Allows parallel processing. It fills them with data. If writing directly to the buffer memory, it needs to wait on any associated sync fences first to ensure it's safe. Once filled, it can insert the packets back into the stream, possibly out of order from how they were received.
Asynchronous packet handling. And how does it tell the consumer the data is ready? The presentation step.
By using synchronization fences. If processing was synchronous, CPU finished, the producer might just wait until it's done before inserting. If asynchronous, like a GPU task, the async API generates a fence that signals completion. The producer attaches this fence to the relevant packet elements using NVSci Stream block packet fence set before inserting the packet. The consumer then knows to wait on that fence before reading the data.
Fences are the key sync primitive. Got it. How are the NVSci channels configured? The ones for interprocess communication.
Typically via a config file, exit nvsipc.cfg. The guide shows a small example with channels defined as interprocess, setting parameters like max packets in flight and max frame size. It also mentions interchip channels using PCIe for communication between different physical chips on the board.
Oh, okay. A system config file manages those IPC channels. There's a performance test app, test NV, SciStream, perf. What can it measure? Any key options?
Yeah, useful tool. Measures latency and bandwidth for various NV SciStream setups. You can test single process unicast multicast, interprocess unicast. Options let you control packet counts in, fix the producer rate in at, run in raw latency mode, save results to CSV, specify buffer sizes, and even test interchip PCIe bandwidth, specifying PCIe channels. Lots of options, LPFV, etc., to benchmark different scenarios.
Great for performance tuning. How are NV slicing fences used at runtime for general synchronization between components?
The basic pattern is a signaler, or AG producer, prepares some work, gets a fence associated with that work's completion, and shares the fence with a waiter, AG consumer. The waiter sets up its own work to depend on that fence being signaled. Both enqueue their jobs. The fence ensures the waiter's job only starts after the signaler's job is finished. Guarantees execution order.
Signaler creates fence, waiter waits on fence, standard dependency management. How do you read from an NV-SciBIC endpoint?
The guide shows using standard Linux select to wait for events on the endpoint's file descriptor. When select indicates activity, you call NVSciIP event safe. If the event type is NVSIP event thread, you know data is available to be read from the endpoint buffer. Event-driven reading.
Okay, standard event loop pattern. What if you need new interchip NVSciP channels over PCIe? How do you add those?
That requires modifying the system's device tree source files, .dtsi. You need to add or modify nodes describing the PCIe root port and endport configurations on the Orin dev kit for the new channel. It points to example nodes. So adding new hardware communication paths involves low-level device tree changes.
Device tree edits, okay.
Yeah,
definitely lower level work. Let's move to NVIDIA. What's its main role in this AV SDK?
NVIDIA provides hardware acceleration for image and video processing on the Drive AGX hardware. Things like decoding, encoding, scaling, format conversion, computationally heavy tasks. It offloads these from the CPU to dedicated hardware engines.
Crucial for handling all the sensor data in real time. It mentions NVMedia loadable and a constraint. Only one loadable per instance. What's a loadable?
A loadable is basically a compiled neural network model, usually created by the tensor builder. It's the binary file the hardware accelerator, like the DLA deep learning accelerator, actually runs.
Okay, the executable model.
And the constraint.
Any single NVMedia instance, like one DLA engine, can only have one of these loadables active at a time. To switch models, you have to call NVMediaSetCurrentLoadable to explicitly load the one you want to use next. The guide also notes the DLA can access all system DRAM and refers to TensorRT docs for memory pool config details. TensorRT Builder also reports which parts of your network compiled successfully and how much memory they need.
Load one model at a time per engine. Got it. What about video encoding with NVMedia? IEP image encode processing. IEP is the NVMedia component for hardware-accelerated encoding. Takes NVMedia images, usually YUV, as input, encodes them into H.264, H.265, or AV1 video formats. The guide mentions H.264 encoding supports YUV input up to 4K resolution. More details are apparently in a separate video encode section.
Hardware encoding for H.264, H.265, AV1, essential for logging or streaming. It shows NVMedia tensor destroy. Why is destroying tensors important?
Standard resource management. NVMedia tensors, multi-dimensional data arrays used for DL, etc., allocate memory. If you don't explicitly call NVMedia tensor destroy, when you're done, you leak memory. Leak's bad. so always destroy what you create.
Cleanup is critical. How does NVMedia sync with other things like CAD or other NVSci sync apps?
NVSci Sync is the glue. It extends NVMedia imaging components to synchronize with CUDA and other NVSci Sync-aware parts of the system, especially important for ADSAV pipelines, less so for general video components. Key functions let you register and register NVSci Sync objects with NVMedia components, NVMedia's XREX register, NVSci Sync of J, and associate AZ Sync object to signal start of frame. NVMedia XXset NVSci Sync of J for ADSOF ensures proper timing across the pipeline.
NVSci sync coordinates NVMedia with the rest of the system.
Got it. There's also guidance from SIPL, Sensor Input Processor Layer, about output image formats.
Right. SIPL handles the camera sensor input. The format of the image coming out of the initial capture stage, ICP, depends on the sensor itself. Specifically, the CA-FA, color filter array, and input format fields in the platform CFG structure, which describes the camera setup, determine the output format. The guide gives examples of the NVSci-buff attributes needed to describe common formats like YUV420 semi-planar or YUV444 pack block linear.
So the platform CFG tells us SIPL about the sensor, which dictates the initial image format. What about camera errors or interrupts, especially in a dual-soak setup? Interesting point. Even if a secondary Orin sock is just in receive-only mode, hardware error interrupts from the camera are typically connected to both socks. SIPL will propagate these error notifications to the client app on the secondary sock too.
So both know there's a problem.
Yeah, but the secondary suits might not be able to do much about it, like perform I2C operations to diagnose or recover the link. Still, knowing there's a fault can be valuable for the secondary application, maybe to halt processing of potentially bad data.
Okay, notification for all, recovery might be primary only. SIPL also provides embedded data and stats like histograms, LAC, flicker. How do developers get that?
Through various SIPL structures. Simple Control Auto Input param is used for input to auto controls and contains fields like embed data, sensor 8, and stats info, which holds histogram, LAC, flicker data. Other structures like Simple Control Auto Ob setting hold white balance info, and Simple Control Stat setting holds ISP stats. You use the SIPL APIs to query these structures.
Okay, specific SIPL structures hold that metadata and statistics. What about noise profile plugins? It mentions max-supported noise profiles.
Noise reduction can use plugins. Max-supported noise profiles just tells SIPL the maximum number of different noise profiles that specific plugin supports. When the plugin's get noise profile function runs, the output profile number must be between 0 and max-supported noise profiles 1. The guide stresses the plugin must validate its inputs and return errors if values are out of range or validity flags like X time valid are false. Plugin developer responsibility.
Plugin needs to do its own validation. Got it. Camera authentication features mentioned too. What kind of security?
Several layers. Camera module authentication is the hardware genuine. Image authentication is the data from the right source, untampered, not a replay. And control authentication are commands sent to the camera, usually over I2C, secure and untampered.
Comprehensive camera security. What if I2C authentication fails?
If it fails during initial camera init, the whole initialization fails. Error returned. If an I2C transaction fails during runtime after initialization, it's reported via the CPL notification queue as a notiferg dicet sensor troll failure event. So init failure is blocking, runtime failure is an error notification.
Okay, different handling for init versus runtime failures. What kind of info does the SIPL query component provide for the platform CFG?
It can give you all the essential hardware config details needed for platform CFG. I2C addresses of devices, image sensor properties, resolution, frame rates, etc., MIPI deserializer properties, and which camera modules are connected to which Orin CSI ports. You can build platform CFG manually, but query is a convenient way to get it.
Query tool helps populate that crucial config structure. What about NVSIPL NITO metadata and get NITO metadata from memory, NITO files?
NITO is NVIDIA Image Tuning Object. These files contain parameters for tuning the image pipeline, color, noise, etc. NVSIPL NITO metadata holds metadata about the parameter sets in a NITO file. An ID, a hash of the parameter structure schema, and a hash of the data itself. Get NITO metadata from memory lets you parse a NITO file loaded into memory and extract this metadata for all the parameter sets it contains. Lets you see what tuning options are available.
Metadata for image tuning files. Got it. This SCPL query app has command line options too. Any useful ones?
Yeah, config file to specify a config, list devices to see detected cameras, show NITO metadata to dump that NITO metadata we just talked about, num parameter sets in NITO to set expectations for NITO files, and use NVSciBuff path to use NVSciBuff inputs instead of NVMedia images. Good options for inspecting the SIPL setup.
Okay. Then there are options for sample apps, NVMe GRAW to UVEV, and NVMe BJPEG deck. Key
For
parameters.
raw to UVO, input raw, msensor link mask, iCrop, input crop, output U file, output resolutions, output format default U420, EDV, downscale factor. For JPEG deck input JPEG deck, output res data format, output format NVIDIA's downscale, plus options for custom huff table and quantization, quantum tables, and IVWED to pick a hardware decoder instance, basic image conversion decoding tools.
Useful utilities. Finally, the NVMe MEPC sample for encoding. It lists a ton of parameters. Common ones, HTART264, HTART265 specifics.
Yeah, and DMAPG uses the IDP API for H265 VP9 AV1 encoding. The common parameters control things like profile, EP profile, frame rate, EP frame rate numbed, bitrate, EP bitrate, rate control buffer, EP BVB buffer size initial delay, initial quantization, BPQ peanut, number of B frames, EP num frames, IDR frame interval, IP2 interval, color space, EP color STD, EP range, EP transfer, S, and a chroma format, EP chroma format, ODZ.
Yeah.
Also quantization for different slice types, QPP slice, QPI slice.
Okay, the fundamental encoding controls.
Then it gets codec specific. For H.264,
Right.
profile level entropy coding, CVL, CFEDAC, feedback into QP offset, constrained prediction flag, deep blocking filter controls, inter refresh, max slice size, adaptive transform mode, SPF RPS, repetition flags. For H.265, profile tier level entropy mode, CBAC, init QP, constrained intra, deblocking controls, inter refresh period, slice counts. Just a huge amount of control.
Wow, really exposes the encoder's capabilities. It also mentions dynamic resolution change, DRC.
Yeah, changing resolution midstream. If you enable DRC buffer realloc, you provide separate input files for before and after the resolution change. It handles the transition, then it lists the NVMEPC command line options themselves. IOO res, output resolution with wide range, HD, etc.
Okay. And it very briefly touches on a few other things.
Just mentions them, yeah.
Yeah.
NVMe optical flow for optical flow estimation, NVMBL sample for using the deep learning accelerator, reporting CSI packet decode errors. The nvlog system log, home NVIDIA nvlog system log.txt, migrating the persistent metadata partition, using version checker root.py to verify software versions.
Right, version checking.
Which Linux services are disabled by default, uPower, Pulse Audio, ALSA, apt2daily, often for resource saving or because they're not needed. Installing other Debian file systems like Drivio's Ubi Desktop after the core install, starting GUI services like GDM3, or using 11VNC for remote desktop.
Remote desktop, okay.
The copy target tool for customizing file systems via manifests. CAN driver support. Tegra CAN based on Bosch MT-TCN, and how to bring up CAN, enable FD mode, use CANDUP, and configure hardware filters via sys. The crypto interface using the virtual SE driver, Tegra HVVC, and standard Linux interfaces. Secure boot setup, generate keys, burning fuses. PKCS Shackle 11 for accessing hardware keys crypto. Encrypted user partitions, EFS, using DM setup. Building flashing custom kernels. Using Yocto to build DriveWorks. Using IndyTramps with read-only roots. Pre-M TRT patches for real-time Linux.
Wow. Okay, rapid fire through a lot of advanced topics there. Boot flow too.
Yeah, boot ROM, DKPSE, BL1, NPR5, microboot 1, MB1, doing clock security, SDRAM init based on BCTs. Boot chain grouping, BCH for authenticating firmware loaded by the same loader. Ratcheting to prevent rollbacks. Pinmux and prod configurations via files or commands. BCT command block structure. Recovery partition naming. Partition table attributes. Device tree source. DTS, DTSI files compiled to DTB. Customizing hardware description like disabling a USB port. Using ptdump for PCT info and tcmuxer. The Tegra stats utility for system resource monitoring. CPU, GPU, memory, accelerators, network. Rate limiting APIs. NVBMAR periodic XX start, anti-rate limit weight. Measuring CPU utilization with vectrace. Example device tree properties for display. Enabling static IMP for QNX, GMSL and DP-Link rate properties. Example device tree node for the GPU. Tegra to D. It's a lot.
That was an incredibly deep dive, wasn't it?
Yeah.
We went from the absolute basics of the Drive OS architecture, setting things up, all the way through, well, NVSci stream, graphics tweaks, power, security, bootloaders, device trees, the whole 9 yards.
It really covers the spectrum. And I think going through the guide like this, even at a high level, you get a real sense of the sheer complexity and the level of detail involved in building the software stack for autonomous vehicles. It's a massive undertaking.
Absolutely. So for everyone listening, we really hope this deep dive has given you a more structured, maybe more digestible path through what can feel like an overwhelming amount of technical information. We try to pull out those key concepts and practical bits that give you that foundational understanding.
Yeah, hopefully you now have a much clearer picture of what's involved in actually developing AV applications on this NVIDIA DRIVE Orin platform. It's powerful, but there's a lot to learn.
We definitely encourage you, if specific areas caught your attention, dive back into the actual developer guide or the related resources it points to.
And maybe just reflect on the engineering challenge here. Building safe, reliable, autonomous systems is incredibly hard, and sophisticated SDKs like this are just absolutely essential tools to make it possible.
Couldn't agree more. Well, thanks so much for sharing this very comprehensive source material with us, and thanks to all of you for joining us on this deep dive. Hopefully it gave you that valuable shortcut to understanding the essentials of the NVIDIA DRIVE OS Linux SDK.
Until next time.